Hachette Audio presents What is Real? The Unfinished Quest for the Meaning of Quantum Physics. Written by Adam Becker. Read by Greg Tremblay.
For Elizabeth, who always knew. The soundest fact may fail or prevail in the style of its telling. Ursula K. Le Guin. Introduction. The objects in our everyday lives have an annoying inability to appear in two places at once. Leave your keys in your jacket, and they won't also be on the hook by the front door. This isn't surprising. These objects have no uncharted abilities or virtues. They're profoundly ordinary. Yet these mundane things are composed of a galaxy of the unfamiliar. Your house keys are a temporary alliance of a trillion atoms, each forged in a dying star eons ago, each falling to Earth in its earliest days. They have bathed in the light of a violent young sun. They have witnessed the entire history of life on our planet. Atoms are epic. Like most epic heroes, atoms have some problems that ordinary humans don't. We are creatures of habit, monotonously persisting in just one location at a time, but atoms are prone to whimsy. A single atom, wandering down a path in a laboratory, encounters a fork where it can go left or right. Rather than choosing one way forward, as you or I would have to do, the atom suffers a crisis of indecision over where to be and where not to be. Ultimately, our nanometer Hamlet chooses both. The atom doesn't split. It doesn't take one path and then the other. It travels down both paths, simultaneously thumbing its nose at the laws of logic. The rules that apply to you and me and Danish princes don't apply to atoms. They live in a different world, governed by a different physics, the sub-microscopic world of the quantum. Quantum physics, the physics of atoms and other ultra-tiny objects like molecules and subatomic particles, is the most successful theory in all of science. It predicts a stunning variety of phenomena to an extraordinary degree of accuracy, and its impact goes well beyond the world of the very small and into our everyday lives. The discovery of quantum physics in the early 20th century led directly to the silicon transistors buried in your phone and the LEDs in its screen, the nuclear hearts of the most distant space probes and the lasers in the supermarket checkout scanner. Quantum physics explains why the sun shines and how your eyes can see. It explains the entire discipline of chemistry, periodic table and all. It even explains how things stay solid, like the chair you're sitting in or your own bones and skin. All of this comes down to very tiny objects behaving in very odd ways. But there's something troubling here. Quantum physics doesn't seem to apply to humans or to anything at human scale. Our world is a world of people and keys and other ordinary things that can travel down only one path at a time. Yet all the mundane things in the world around us are made of atoms, including you, me, and Danish princes. And those atoms certainly are governed by quantum physics. So how can the physics of atoms differ so wildly from the physics of our world made of atoms? Why is quantum physics only the physics of the ultra-tiny? The problem isn't that quantum physics is weird. The world is a wild and woolly place with plenty of room for weirdness. But we definitely don't see all the strange effects of quantum physics in our daily lives. Why not? Maybe quantum physics really is only the physics of tiny things, and it doesn't apply to large objects. Perhaps there's a boundary somewhere, a border beyond which quantum physics doesn't work. In that case, where is the boundary? And how does it work? And if there is no such boundary, if quantum physics really applies to us just as much as it applies to atoms and subatomic particles, then why does quantum physics so flagrantly contradict our experience of the world? Why aren't our keys ever in two places at once? 80 years ago, one of the founders of quantum physics, Erwin Schrödinger, was deeply troubled by these problems. To explain his concerns to his colleagues, he devised a now famous thought experiment: Schrödinger's cat. See Figure 1.1. Schrödinger imagined putting a cat in a box, along with a sealed glass vial of cyanide with a small hammer hanging over the vial. The hammer, in turn, would be connected to a Geiger counter, which detects radioactivity, and that counter would be pointed at a tiny lump of slightly radioactive metal. This Rube Goldberg contraption would be set off the moment the metal emitted any radiation. Once that happens, the Geiger counter would register the radiation, which would release the hammer, smashing the vial and killing the cat. Schrödinger had no intention of actually conducting this experiment, to the SPCA's relief. Schrödinger proposed leaving the cat in the box for a certain period of time, then opening the box to find the cat's fate. The radiation emitted by the lump of metal is composed of subatomic particles, breaking away from the atoms in the metal and flying off at high speeds. Like all sufficiently tiny things, those particles obey the laws of quantum physics. But instead of reading Shakespeare, the subatomic particles in the metal have been listening to the clash. At any particular moment, they don't know whether they should stay or they should go. So they do both. During the time the box is closed, the indecisive lump of radioactive metal will and won't emit radiation. Thanks to these punk rock particles, the Geiger counter will and won't register radiation, which means the hammer will and won't smash the vial of cyanide. So the cat will be both dead and alive. And this, Schrödinger pointed out, is a serious problem. Maybe an atom can travel down two paths at once, but a cat certainly can't be both dead and alive. When we open the box, the cat will either be dead or alive, and it stands to reason that the cat must have been one or the other the moment before we opened the box. Yet many of Schrödinger's contemporaries piled on, denying exactly that point. Some claimed that the cat was in a state of dead and alive until the moment the box was opened, when the cat was somehow forced into aliveness or deadness through the action of looking inside the box. Others believed that talking about what was going on inside the box before it was opened was meaningless, because the interior of the unopened box was unobservable by definition, and only observable, measurable things have meaning. To them, worrying about unobservable things was pointless, like asking whether a tree that falls in the forest makes a sound when nobody's around to hear it. Schrödinger's concerns about his cat weren't allayed by these arguments. He thought that his colleagues had missed the point. Quantum physics lacked an important component, a story about how it lined up with the things in the world. How does a phenomenal number of atoms, governed by quantum physics, give rise to the world we see around us? What is real at the most fundamental level, and how does it work? Yet Schrödinger's opponents carried the day, and his concerns about what was actually happening in the quantum world were dismissed. The rest of physics simply moved on. Schrödinger was in a minority, but he wasn't alone. Albert Einstein also wanted to understand what was really happening in the quantum world. He debated Niels Bohr, the great Danish physicist, over the nature of quantum physics and reality. The Einstein-Bohr debates have entered into the lore of physics itself, and the usual conclusion is that Bohr won, that Einstein's and Schrödinger's concerns were shown to be baseless, that there is no problem with reality in quantum physics because there is no need to think about reality in the first place. Yet quantum physics is certainly telling us something about what is real out in the world. Otherwise, why would it work at all? It would be very difficult to account for its wild.
Sample complete. Ready to continue?